You have lived your entire life inside an experiment, and nobody ever told you it was running. Every second since the day you were born, something has been pulling on you, pulling on the blood in your arteries, on the marrow in your bones, on the fluid behind your eyes, on the air you are breathing right now in this very room. And it has done this with such patience, such absolute reliability, that your brain wrote it off as background noise before you were old enough to form a single question about it. So let me start by saying something that is going to annoy at least half of you. You do not understand gravity, you are used to it. And those are not the same thing, not even close. I am going to spend the next hour proving that to you, and I am going to do it by asking what looks like a child's question and refusing to let either of us off the hook until we have followed it all the way down. Here is the question: what would happen if Earth's gravity doubled overnight? You went to sleep, the number was 1. You woke up, the number was 2. Simple. And I can already see some of you reaching for the easy answer. Everything gets twice as heavy, things fall down, it's bad, the end. No, stop. That is exactly the kind of answer that has set physics back 300 years at a time, and I am not going to let you have it. Because before I can tell you what happens, I have to ask you something back, and your inability to answer it is the first lesson of the night. What do you actually mean when you say gravity doubled? You don't know. You haven't told me how. And I promise you, the how is not a footnote. The how is half the universe. Let me show you what I mean. Newton handed us the equation more than 3 centuries ago, and it is so clean it almost looks like a trick. The pull you feel at the surface of a world depends on 2 things, and 2 things only: the mass of the world and how far you are from its center. Write it as the mass divided by the distance squared, throw in a constant of nature to set the scale, and that is your weight. That is the whole story of standing up in the morning. So if I tell you gravity doubled, I am telling you that this number, this acceleration that has held you to the floor your entire life, and which on Earth runs to about 9.8 meters per second every second, has jumped to 19.6. Fine. But there are at least 3 completely different ways to make that happen, and they do not lead to the same morning. They barely lead to the same planet. Way number 1, you double the mass of the Earth while leaving it exactly the same size. Cram twice the material into the same ball. Way number 2, you keep all the same material but shrink the Earth. Squeeze the radius down by about 30%, and because the distance is squared in that equation, the pull at the new closer surface climbs to double. Way number 3, the cheater's version, the one in the comic books. You leave the Earth completely alone, same mass, same size, and you just reach in and twist the universal constant of gravitation itself, the dial that sets how strongly mass talks to mass everywhere, in every star, in every galaxy, all at once. 3 doors, and here is where it gets strange. For the first time tonight, because the person who walks through door 1 and the person who walks through door 2 and the person who walks through door 3 all step out into a different catastrophe. Walk through door 3, the magic dial, and you have not changed the Earth. You have changed the sky. The sun is held together by a war, a standoff between its own gravity trying to crush it into a point and the heat of fusion trying to blow it apart. Turn up gravity everywhere and you have just tipped that war. The sun contracts, burns hotter. The orbits of every planet tighten. The whole architecture of the solar system lurches. Your doubled weight on the bathroom scale would be the least of your problems, because the thing in the sky that grows your food and warms your oceans just had its constitution rewritten. So let us be honest and set door 3 aside, not because it's uninteresting, but because it isn't really a question about Earth anymore. It's a question about whether physics itself can be edited. And the honest answer is we have no idea, because as far as anyone has ever been able to measure, that constant has been the same number since the universe was a few minutes old. So we are left with doors 1 and 2. And the most charitable, most useful reading of your question, the one a working physicist would actually sit down with, is this: the downward tug at the surface doubles. Your weight doubles. Now we can do some honest work. And I want to begin where I always begin, which is with the thing right in front of you, your body. Because before we talk about planets and orbits and the bending of time, which we absolutely will, I want you to feel this in your own chest first. You weigh, let's say, 70 kilograms. The day the gravity doubles, you do not gain a gram of flesh, but you weigh as much as a 140-kilogram person. And I don't mean you're carrying a backpack. I mean every organ inside you is now twice as heavy. Your heart is a pump that evolved over hundreds of millions of years to push blood uphill against exactly one unit of this stuff. One. It has never met two. The moment you stand up, the blood in your body wants to pool in your legs with twice the eagerness it ever had, and your heart has to fight twice as hard to send it back up to your brain. For a lot of people in this room, the very old, the very sick, the ones with hearts already working at their limit, standing up that first morning is the last thing they ever do. They faint. Some of them don't get back up. And here is the cruelty of the word overnight. There is no time to adapt. Biology adapts over generations, not over a single sleep. Now I want to kill a misconception, because if I don't, somebody's going to leave here repeating it, and I have spent my whole career chasing misconceptions out of rooms like this one. People imagine that at double gravity your bones simply shatter under your own weight, that you collapse like a dropped vase. That is wrong, and the truth is more interesting. Your thigh bone, your femur, is an astonishing piece of engineering. It can bear loads of thousands of newtons in compression, many times your body weight with margin to spare. Standing still at double gravity will not snap it. So what actually gets you? Not the standing, the moving, the falling. Watch what happens to a stumble. At normal gravity, you trip, you fall, you hit the ground with a certain amount of energy, and most of the time you get up swearing. The energy you arrive with depends on your weight and the height you fell from. Double the gravity, and you have doubled the energy of every single fall. And worse, you fall faster, so you have less time to throw out an arm or twist away. A tumble down a flight of stairs that would have bruised you yesterday breaks your hip today. A fall from a ladder that would have been a story to tell becomes a fatal one. The danger was never your bones quietly bearing your weight. The danger is the violence that gravity adds to every accident, and overnight, the whole world becomes an obstacle course built for a creature half your effective weight. Breathing is harder because your diaphragm has to lift a heavier chest with every breath. Walking is exhausting, like wading through your own life. We have spun people up to 2 gravities in centrifuges, and a fit human can endure it, can even work in it for a while. But to live in it every minute, every day, with no break and no escape, is to be slowly, relentlessly ground down. Now hold that thought, because here comes the part that surprised even me when I first worked it through. Everything I just described, the falling, the strain, the exhaustion, applies equally to a feather and a cannonball. And that is one of the strangest and most beautiful facts in all of physics, and it took humanity an embarrassingly long time to see it. We headed backwards for 2,000 years. Aristotle, brilliant as he was, told the Western world that heavier things fall faster. And because it sounds obvious, because it matches what you think you see when you drop a stone and a leaf, nobody seriously challenged it until a stubborn Italian named Galileo Galilei came along and did something radical. He didn't argue, he measured. And what he found, what he established by rolling balls down ramps to slow gravity down enough to actually clock it, is that in the absence of air resistance, all objects fall at exactly the same rate, regardless of their mass. The feather and the hammer hit the ground together. If you don't believe me, you don't have to believe me. We tested it on the moon. In 1971, an astronaut named David Scott stood on the airless surface of another world, held out a falcon feather in one hand and an aluminum hammer in the other, and let them go. They fell side by side and landed at the same instant, and you can watch the film of it to this day. So in our doubled gravity world, here is the precise truth. Every object still falls at the same rate as every other object. What changes is that the shared rate doubles. The whole universe of falling things speeds up together in lockstep. The feather and the cannonball still perfectly matched, just both arriving sooner. And the reason that is so profound, The reason it kept Galileo and then Newton and then Einstein awake at night is that it tells you something is suspicious about gravity. It does not care what you are made of. It pulls on everything in exact proportion to how much there is of it, so that the heavier thing, which is harder to get moving, is pulled correspondingly harder, and the two effects cancel perfectly. Perfectly. In all of physics, when two things cancel that perfectly, it is never an accident. It is a clue. Hold on to that clue. We are going to need it at the end of the night. But let us climb back out of our own bodies and look around the room, the world, the biosphere, because we are not the only things that have to negotiate with this number, and most of life negotiated a very different deal than we did. Go back to that same stubborn Italian, Galileo, at the end of his life, under house arrest, half blind, and writing what may be the most underrated book in the history of science, The Two New Sciences. And in it, he asks a question that sounds like it belongs in a fairy tale, but is pure, hard physics. Why are there no giants? Why can't you simply take a man and scale him up to the size of a tower and have him walk around? And Galileo answered it. 300 years before anyone built a skyscraper, with an argument so clean it still governs engineering today. Here is the argument, and it is the secret key to half of tonight. When you make a creature bigger, its weight grows with its volume, which is to say, with the cube of its size. Double the height, and you have roughly 8 times the weight. But the strength of its bones, the strength of any column or beam, depends on the cross-sectional area, the thickness, which grows only with the square of its size. Double the height, and the bones are only 4 times as strong. So strength falls behind weight, always, relentlessly. The bigger you get, this is why an ant can carry many times its body weight, and an elephant can barely manage to jump at all. The elephant is not weak. The elephant is enormous, and it is living right up against the structural limit that its bones can bear. It is a building that has run out of safety margin. Now, here is where it gets strange. Double the gravity, and you have effectively doubled the weight of every living thing while leaving its bones exactly as strong as they were yesterday. You have shoved every large animal on Earth past its limit in a single night. The elephant, the rhinoceros, the giraffe, the great whales who think they escaped gravity by floating, but who would be crushed by their own mass the moment they were stranded, all of them are suddenly creatures whose skeletons can no longer reliably carry them. The small things, the insects, the mice, the sparrows, they barely notice. They had margin to burn. It is the mighty who fall first, and there is a strange and ancient justice in that. And it isn't only animals. Look at the tallest living things on the planet, the great redwoods of California reaching 300 feet and more into the sky. Why do they stop there? Why not 1,000 feet? Part of the answer is that water can only be pulled so high through their veins before the column breaks, but part of it is pure Galileo. A tree is a column fighting gravity, and there is a height at which a column of a given thickness will simply buckle under its own weight, like a stalk of wheat that has grown too tall. Double the gravity, and you have lowered that ceiling. The tallest trees on Earth, the ones that took 2,000 years to climb that high, are now standing taller than the new physics permits. Over the seasons that follow, the giants of the forest come down. And I want you to notice the pattern that is forming, because it is the real lesson hiding inside this whole thought experiment. Gravity is not just a force. It is the editor of life. It decided how big you could get, how tall a tree could grow, how thick a leg bone had to be, how a heart had to be plumbed. Change the number, and you have not merely made things heavier, you have invalidated 4 billion years of design. Let me give you a real example of how that editing works from a world I happen to know something about, because I have spent a good part of my career staring at it. Mars. Mars has only about a third of Earth's surface gravity. And on Mars sits a mountain called Olympus Mons, a volcano that rises nearly 70,000 feet, more than twice the height of Everest, so wide that if you stood at its base, you could not see its peak over the curve of the planet. How does Mars get away with a mountain that obscene? Because on a low-gravity world, rock can pile up higher before its own weight causes the base to deform and slump and flow. The maximum height of a mountain is set by a tug of war between how strong rock is and how hard gravity is pulling it down. So now run the logic backwards onto our doubled Earth. The mountains we have, the Himalayas, the Andes, the Rockies, are too tall for the new gravity. They are not in trouble overnight. Rock is patient, but over the long geological haul, they will sag and settle and grind themselves lower, and the new Earth will be a flatter, more crushed down version of the one we knew. A world has the mountains its gravity allows, and no taller. That is not poetry. That is rock mechanics, and you can compute it. And while we are talking about what gravity edits, consider the most defiant trick life ever pulled, the one that always struck me as nature's open rebellion against this whole conversation: flight. A bird stays up by throwing air downward hard enough to hold its own weight against the pull, and there is a brutal arithmetic in that, which is why the heaviest birds that truly fly, the great bustards and swans and condors, sit right at the edge of what is possible, laboring to get airborne, while anything heavier gave up and learned to run. Double the gravity, and you have moved that edge sharply inward. The large flyers are grounded in a single morning, their wings now hopelessly undersized for a body that weighs twice what it did. Only the smallest, the sparrows and the insects, keep their place in the air, and even they work harder for it. So picture, if you can, what life would have looked like had it grown up under this heavier sky from the very beginning. Not taller, but squatter, thick-limbed, low to the ground, broad-footed, built like wrestlers rather than dancers. Few tall trees, perhaps no real forests as we know them, and a sky emptier of wings. I spent a good part of my life wondering what life might be like on other worlds, and this is the heart of that question. Biology is not free to be anything it likes. It is a negotiation with the local gravity signed in bone and wing, and a heavier world writes a heavier, lower, more cautious kind of life. Now, what about everything we built? Our bridges, our towers, our homes? Engineers are not fools. They build with safety factors. They build a structure to bear several times the load it will ever normally see, so a doubling does not automatically mean instant collapse. But it means the safety margin you paid for is gone, eaten in a single night. The dead load, the weight of the structure carrying itself, has doubled before you have put a single person or car or stick of furniture on top of it. Bridges that were rated for certain traffic find that their own steel and concrete is now eating most of their strength. The most heavily loaded structures, the longest spans, the tallest towers, the ones already operating closest to their limits, are the ones that fail, and they fail in the worst possible way, suddenly and without warning, because the load did not creep up on them, it doubled while everyone was asleep. And here is where it gets strange again, in a way that has nothing to do with steel. I have not yet said one word about the most important thing in the room. The air you are breathing right now without thinking about it, and the air you are pulling into your lungs is not weightless. There is a column of atmosphere standing on top of you, miles high, and it has weight, and that weight pressing down is what we call air pressure. Roughly 14.5 pounds on every square inch of you, which you do not feel only because you are pressurized from the inside to match, now double the gravity. That entire column of air just got twice as heavy. The pressure at the surface climbs toward double what it is now, 2 atmospheres. The kind of pressure you would feel diving 30 feet underwater, except now it is everywhere all the time, the new sea level of a heavier world. And the air does something else, something subtler. It crouches. The atmosphere puffs up to the height it does because the warmth of its molecules fighting to spread out is balanced against gravity pulling them down. Strengthen the gravity and the air pulls in tighter to the ground. The comfortable layer of breathable atmosphere, which thins out over a scale of several miles today, would compress to roughly half that height. The mountaintops that were merely cold and thin yesterday become genuinely, lethally airless. The breathable world gets shorter. I want to pause here and tell you something personal, because this is exactly the kind of mistake that taught me to respect this material. Early in my life as a scientist, I was fascinated by Venus, our sister planet, almost exactly the same size as Earth, almost exactly the same gravity. And the temptation, the deep human temptation, was to reason by analogy. Same size, same gravity, surely a similar world. People imagine Venus as a warm, swampy place, maybe dripping jungles under the clouds. And then we actually went and looked, and we found a surface hot enough to melt lead, nearly 500 degrees, crushed under an atmosphere 90 times heavier than ours, a runaway greenhouse that had turned a near twin of Earth into a vision of hell. I had to learn the hard way that your intuition is a liar. The universe does not care what seems reasonable to a primate raised on one particular planet. And that is the lesson I am asking you to carry through this whole exercise tonight, because every time you say, obviously this would happen, you are reasoning like someone who expected Venus to be a swamp. The only way through is to lay every brick yourself and refuse to trust the picture until the physics has built it for you. So let us lay the next brick, and it is the one most people get spectacularly wrong, because it is the one where the difference between door 1 and door 2 finally comes back to bite us. What happens to the moon? What happens to the satellites, the space station, the thousands of things we have flung into orbit? And the answer depends entirely, completely on which door we walked through. And I told you at the start that the how was half the universe. I was not exaggerating. Here is the subtlety. The moon does not care about the gravity you feel on Earth's surface. The moon, hanging 240,000 miles away, responds to one thing only, the total mass of the Earth. So suppose we walked through door 2, the door where we shrank the Earth down to make the surface gravity double but kept all the same material. The moon feels no difference at all. The total mass of the Earth never changed, just got packed tighter, and from the moon's great distance, a tighter ball of the same mass pulls exactly as it always did. The moon sails on, serene, oblivious. The tides change a little because the oceans themselves are heavier, but the moon keeps its orbit. Now walk instead through door 1, where we doubled the actual mass of the Earth. Now everything in the sky is in trouble. The moon is suddenly being pulled toward an Earth twice as massive, with twice the grip, while it is still moving at the same lazy speed it had yesterday, a speed that was perfectly tuned to balance the old, weaker pull. That speed is no longer enough. The moon begins to fall inward, its circular path collapsing into a tightening, plunging ellipse, swinging closer and faster. And the gentle gravitational conversation between Earth and Moon that has lasted 4 billion years and slowly shaped the length of our day becomes something violent and unstable. And forget the moon for a moment. Think about what we have put up there ourselves. The International Space Station, every weather satellite, the entire constellation of GPS spacecraft that your phone is quietly listening to right now to tell you where you are, every one of them is in orbit because of a precise bargain. They move sideways at exactly the speed needed so that as they fall toward the Earth curves away beneath them just as fast and they fall forever without ever hitting the ground. That is all an orbit is. It is the art of missing the planet. Double the mass of the Earth and you have broken the bargain. The pull is now too strong for their speed. They are no longer missing the planet. They begin to spiral down, the space station first among them. And within a span of time that an orbital mechanic could calculate to the hour, the sky we worked a century to populate comes raining back down. The how, you see, was never a footnote. And there is a cruel little twist in door 1 that I cannot resist showing you, because it closes a door we like to imagine is always open. Escape. The speed you need to throw something fast enough that it never falls back, that it climbs away from the Earth forever, is what we call escape velocity. And right now it is about 7 miles a second. 11 kilometers a second, the speed our biggest rockets claw their way up to with enormous violence and enormous expense. Double the mass of the Earth, and that escape speed climbs by a factor of the square root of 2 to nearly 16 kilometers a second. That does not sound like much. It is everything, because the energy a rocket needs, the fuel, the brute cost of leaving, does not climb by 40%. It climbs far faster than that, because of the merciless mathematics of rockets, where every extra bit of speed demands fuel, and that fuel has weight that demands more fuel to lift it. On a doubled Earth, getting to orbit becomes so expensive that it might simply never have been worth it. And here is the thought that genuinely unsettles me. A civilization that arose on a heavier world might look up at the same stars we do, feel the same longing we feel, and find the door to space quietly, permanently closed. They would be prisoners of their own planet, and they might never even know it, because nothing in their everyday life would tell them the cage was there. We are not on such a world. We got lucky. We could leave. We sent Voyager, and that brings me to the deepest part of all this, the part I have been building toward all night. Because I have been talking to you about gravity as a force, as Newton taught us, a pull between masses across empty space. And Newton's law is magnificent. It landed our spacecraft on other worlds. It predicted planets we had never seen. But there is something Newton himself confessed he could not explain, and to his eternal credit, he refused to pretend otherwise. He could describe how gravity behaved, the precise mathematics of the pull, but he could not say what it was. How one body could reach across millions of miles of nothing and tug on another with no rope between them. And when his critics pressed him on it, he wrote one of the most honest sentences a scientist has ever written: "I frame no hypotheses." Meaning, I will tell you exactly what it does, and I will not insult you by inventing a story about what it is when I do not know. For 200 years, that was where it stood. Gravity worked, and gravity was a mystery, and physicists made their peace with describing a thing they could not explain. And then came a clerk in a patent office in Switzerland, daydreaming, and he had what he later called the happiest thought of his life. Albert Einstein imagined a man falling freely off a roof, out of a window, and he realized something that should have been obvious for centuries and somehow wasn't. The falling man feels no gravity. He feels nothing pulling on him at all. He floats, weightless, just like an astronaut, because he and everything around him are falling together at exactly the same rate. Remember Galileo's clue, the one I told you to hold on to? That gravity pulls on everything in perfect proportion to its mass so that all things fall together? This is where that clue pays off. Einstein took it and turned the whole picture inside out. If everything falls at the same rate, then maybe gravity is not a force pulling things down at all. Maybe gravity is what it feels like to move freely through a space that has been bent. Here is the thought experiment, and it is the most important one of the night, so stay with me, lay the bricks. Imagine you are sealed inside a windowless room, and you feel your normal weight, your feet pressed to the floor. Now I ask you, are you standing on the Earth, or are you in a rocket out in deep space, far from any planet, with its engines firing to accelerate you upward at exactly the rate that mimics gravity? And Einstein's staggering answer is that there is no experiment you can do inside that sealed room to tell the difference. None. Gravity and acceleration are not just similar, they are locally the same thing, which means that the doubling of Earth's gravity that we have spent all night exploring is, in the most precise physical sense, indistinguishable from the entire planet becoming the floor of a rocket that has suddenly doubled its thrust, pressing up against the soles of your feet at 19.6 meters per second squared. You are not being pulled down harder. You are being pushed up harder by a floor that is, in Einstein's geometry, perpetually accelerating through curved space-time. Let that sit in your chest for a moment. The most familiar sensation in your entire life, the feeling of your own weight, is the feeling of space-time being curved by the mass beneath you and you pushing back against it. And if gravity is the curvature of space-time, then doubling it does something that sounds like science fiction, but is measured, real, and engineered into the device in your pocket. It bends time. A clock deep in a gravitational field, down in the curve, runs slower than a clock far away from any mass. This is not a metaphor, and it is not a malfunction. It is real. The GPS satellites I mentioned have to correct for it constantly because their clocks, higher up in shallower gravity, tick faster than the clocks on the ground, and if engineers did not account for that difference, your navigation would drift off by miles within a day. So on our doubled gravity Earth, time itself runs a hair slower at the surface than it did the night before. The effect is staggeringly tiny, far too small to feel a difference in the deepest decimal places. But it is not zero. And the fact that it is not zero is the whole point. It tells you that gravity is not some superficial property of heavy things. Gravity is woven into the rate at which time passes. Change the gravity, and you have, however slightly, retuned the clock of the universe at your feet. The question, what would happen if gravity doubled, turns out to be, when you follow it all the way down, the question, what would happen if we bent space-time harder and slowed time itself? And that is not a child's question anymore. Now I owe you a confession, the kind I think every honest scientist owes an audience, because I have spent my career fighting people who pretend to certainty they have not earned, and I will not become one of them on this stage tonight. For all of this, for Newton's beautiful law and Einstein's gorgeous geometry, for the curved space-time and the bending of time that we can measure to absurd precision, we still do not know what gravity actually is at the bottom. Einstein gave us gravity as the shape of space. The rest of physics, the world of the very small, the atoms and the particles, runs on a completely different rule book called quantum mechanics, a rule book of probability and jitter and discreteness. And these two descriptions, the smooth, curved space-time of gravity and the jittery quantum world of everything else, do not get along. They contradict each other in the places where they are forced to meet, at the heart of a black hole, in the first instant of the universe. We have been trying to marry them for the better part of a century, the best minds we have, and we have not done it. There is no accepted theory of quantum gravity. We do not know what gravity is made of, or whether that is even a sensible question. The most familiar force in your life, the one holding you to that chair, is at its foundation the deepest unsolved problem in physics. And I want to tell you that this does not comfort me. I want to be clear about that because there is a soft, lazy way of talking about mystery that treats it as something cozy, something to wrap yourself in. That is not what I feel. What I feel is something sharper and far more productive. I find it deeply, wonderfully unsettling that the thing I have leaned on my entire life, the thing that shaped my bones and my heart and the trees outside my window and the orbit of the moon, is something we cannot yet explain. It is unsettling the way the edge of a map is unsettling, the way that blank space marked unknown is an invitation rather than an insult. The discomfort is the engine. A scientist who is comfortable has stopped working. Let me bring this back to the ground one last time, because I have not survived a career of being called a mere popularizer, of being told that explaining things to ordinary people somehow makes them less true without learning to land the plane. There are colleagues, serious people, who look down on the work of standing in a room like this and saying, here is the universe, let me show you how it really works. There were honors I was kept out of for the crime of believing that the public deserved the real thing and not a watered-down cartoon. And I will tell you what I told myself then. The universe is not diminished by being understood. It is the people who keep it locked away who diminish it. So I have spent my life trying to hand it over intact, hard parts and all. And here is what tonight's impossible question hands over to you. You came in thinking gravity was the most boring thing in the world, the most settled, the most taken for granted, the very definition of nothing to see here. And we have found, by the simple act of asking what if it doubled and refusing every easy answer, that gravity is the silent author of nearly everything you are. It set the size of your body and the plumbing of your heart. It capped the height of mountains and the reach of the tallest trees. It decides whether a world's children can ever leave home and touch the stars, or whether they are sealed in for good. It bends the very passage of time at your feet. And at its foundation, it remains the greatest unsolved mystery we have. All of that hiding inside a number so constant that you stopped noticing it before you could speak. So I will leave you not with an answer, but with the thing that should keep you up tonight. We have spent this hour imagining the disaster of gravity changing. But the truly strange fact, the one I want lodged in your chest on the drive home, is the opposite one. Gravity has not changed. Not by a measurable fraction, not in your lifetime, not in the 4 billion years of life on this planet, not since the universe was minutes old. Every catastrophe we imagine tonight is a measure of how exquisitely, how dangerously, how completely Your existence is balanced on the constancy of a number you never chose and do not understand. You are not standing on solid ground. You are standing on a coincidence that has held. And the question is not what would happen if it doubled. The question is, now that you know what is riding on it, how can you ever again call it boring? Go home. Argue about that.